when I get to the written part, I'm not writing it. I'm just going to let you pause things so that you can write things down at your own speed. So you won't have to sit through me writing this endless thing. Actually, where we're headed, you're going to have to do a lot of writing. And really, when we're doing inference and confidence intervals for proportions, that's the one where we do the most writing. The inference for means, the chi-square, the other stuff that we do, we have to write, but not quite as much as we have to do here. So anyway, we are at a transition. What we did for chapter 17 with our latest quiz is related to this. It's kind of a precursor when we worked with sampling distributions, but this is going to take it much, much further, and it's really going to be, to me, the best part of the course, I think. I think it's the most interesting, and pretty much everything we've done before this will have led up to where we are now. So we're going to start with confidence intervals. And what confidence intervals do is help us to estimate population parameters. Since we're doing proportions, we had talked about how we would know what the true population proportion would be to take a whole lot of samples and try to start approaching building a sampling distribution, average all those proportions, and we'd start seeing ourselves zero in on the true value for P. Well, that's a lot of effort and a lot of time spent and possibly a lot of money. This is like a one-shot deal for using a sample value p hat to estimate the population parameter P. So in this slide you can see here is your formula for the standard deviation sigma sub p hat of your sampling distribution for proportions. And it's just the square root of the population proportion times 1 minus that over n. The problem is, if we're going to use this to estimate the population proportion, how could we possibly know what it is so that we can plug it into this formula? I mean, it just can't be done. It's just not logical. So you may think that that'll be considered to be kind of a block for us, but it really isn't. We're not stuck, not really. We're going to use sample statistics like I've always advertised we would to estimate population parameters. Whenever we estimate the standard deviation of a sampling distribution, we call it standard error. And the way that we get standard error is that we replace P for the population here and here with some sort of a sample outcome. So it's p hat times 1 minus p hat over n. Take the square root of that, and that's called your standard error of p hat. Going back earlier, hang on, this is the standard deviation of p hat, right? The assumption is you know what the population parameter is. Since we're trying to figure that out, we should not know it ahead of time. So now this is it. So there it is. That's your sampling standard deviation for sampling distribution of p hat. We won't know p if we're trying to estimate it, so it becomes standard error of p hat, and we replace p with the sample proportion. Okay, now that we've gone over that, we're going to look at the 68, 95, 99% rule. Remember that, the empirical rule? The reason that we can start pulling this in is because a sampling distribution for p hat, or a sample distribution for proportions, is approximately normal, okay? So it will cut up like any normal curve, where if you take the mean, which will be the population parameter P, and go to one standard deviation to either side of it, you will capture 68% of all the samples. So it'll have p hats within one standard error of p. All right, 95, remember that's plus or minus 2 standard deviations, in this case standard errors. About 95% of all samples will have p hats within 2 standard errors of p, and then about 99.7 will have, of the samples, will have p hats within 3 standard errors of the mean. Okay, great. So this is a convenient way to get a quick grasp of numbers of standard deviations or standard errors. We need that for what you're about to see. Now, just before we move, 68%, if we're going to do a confidence interval with that percentage of success, that's kind of small. So we're not using 68%. And 99.7 seems a little arbitrary, kind of like, well, why not 99.6 or 99.8? Like, what's special about that? So we're not using that either. We will use this, the 95%. So we'll look at the p-hats from that point of view. So consider what we will take out of that, the 95% level. Okay, if we start out with p-hat as the center of our estimate, and we move out 2 standard errors in either direction, so it'll be p-hat plus 2 standard errors on the high end, and then p-hat minus 2 standard errors on the low end, we will get a range of values from low to high that we can be 95% confident will contain the true proportion. All right? Keep in mind that when you center this on p-hat, well, p-hat is a variable because it's a variable quantity because it comes from sampling, and there's always variation in sampling. So you may not get the same p-hat from each sample that you take. So your range of values will shift up or shift down. But if we could do all possible, we'll call them intervals, from all possible p-hats, plus or minus 2 standard deviations, then 95% of them will capture p, and 5% won't. So it's not a perfect thing, but 95% confidence is pretty good. It's like, yeah, you can expect to actually accurately predict the population parameter in 19 out of 20 of these intervals that you would build. And then 1 out of 20 will miss. So that's not bad. So that's what we mean by a 95% confidence interval. And it looks like this. See the happy guy here? He's demonstrating this. So you get a sample proportion from some kind of sample that you take. You then add 2 standard errors, or 2 standard deviations when we don't know what p is. And you subtract 2 standard errors. You will then expand to a interval, low to high, and you can be 95% confident that you can predict, or not predict, but estimate the true value of p. So reaching out 2 standard errors, I gotta say that right, 2 standard errors on either side of p-hat makes us 95% confident we'll trap the true proportion p. All right, so what does 95% confidence really mean? Well, like I said, every confidence interval you generate uses a sample statistic to estimate a population parameter. The exact center of every confidence interval is that sample estimate, in this case p-hat, in the next chapter mu, okay? So it's the sample estimate plus or minus a margin of error. And just glancing back here, 2 standard errors above and 2 standard errors below constitute that margin of error, okay? So, since samples vary, the statistics we use will also, and thus the confidence intervals we construct will vary as well. So, it's not likely that if we sample differently, that we would see 2 exactly the same confidence intervals. So that's where this error comes in, where you're 95% successful in this process, but maybe 5% not successful at a 95% confidence level. So our confidence rather, is in the process that we use to construct the interval, not in one interval all by itself. So if it's a 95% confidence interval procedure, we would expect 95% of all of them that we could possibly build to contain the true parameter that we are estimating. So be careful. If you generate a single interval, don't say there's a 95% probability that it will capture the true value of the parameter. No. Either it did, that's 100%, or it didn't. That makes it 0% successful. Okay, the 95% is our confidence in the process that builds these intervals. So we'll talk about that a little bit more. All right. Okay, this is in your packet. All right, it's on, I think it's page 3. So I'm not going to talk to you about it. We're directly off of this PowerPoint. We'll just turn to the packet page. And this is the homework. So I'm going to go ahead, and it's already posted a number of places. So I'm going to go ahead and get out of here. And I'm going to open up, this is what page 3 looks like. Okay, this will give me a chance to talk to you about some of the details. And again, I wrote all this out for every class 5 times, and they all wrote it with me. It was pretty tedious. So what I need for you to do is when I start referring to the various sections, then pause it, copy down what's there for your notes, and then resume. All right, so the problem that we're going to do is this, what it says up here, 73% of first-year college students responding to a national survey identified being very well off financially as an important personal goal. Okay, fine. This is really, as you will see is when we read the rest of this, not what the problem is engaged in, although there will be a question at the end that will, address that 73%. But what it really talks about is a state university. So it's just one. It finds that 132 of a simple random sample of 200 of its first-year students say that goal is important. Okay, so they want us to give a 95% confidence interval for the true proportion of all first-year students at this university who would identify as being well off as an important goal. Right? It's everything that we're doing concerns a single university. So this 73% in a national survey has nothing to do with what we're about to do until we reach the end, when they ask you something different. Okay. So let's see. If you look down at number 3, I wrote down what p hat was. It's right here. This is p hat is 132 over 200 or 0.66. Okay. So that's what I just wanted to point out from here. And it says it's of a simple random sample. That's important. So the first step, and what I'm going to do is give you the process. And I'm going to give you a script to follow. And I would like for you to follow it. It's what AP wants, what College Board wants. It seems like a tedious amount of extra work and verbiage, but sorry, this is the way it's supposed to go. So I know it's a GT class as well as an AP class, which implies you can be creative. I just see too many novice students get so creative that they go way off track and they don't really report what's needed. So just use this. You've been warned. All right. Define the parameter. We have to do this for all the inference, whether it's confidence intervals or test of significance or what. So here it is. P is the true proportion of first-year college students at this state university who identify being well off financially as an important goal. I don't think you can read that and fail to figure out what I'm talking about. All right? So that's the reason that everything is there. So you're actually writing for an audience. It's not enough that you know what's going on. You're communicating to others what's going on. So pause if you need to. All right, the next thing to do is to list and verify assumptions. This is what we were doing when we had the 2 rules of thumb for the sampling distribution for proportions. Okay. Now, I have this a little out of order to what I normally do. The first thing I typically do is check for randomness, because while that wasn't one of our rule of thumbs, it is one of our 3 assumptions for inference, for proportions. So, it says up here, a simple random sample of 200. So, SRS is given. Now, if they don't say that things are random, but you think they are, for example, if I'm doing a study on some kind of soil aspect, and I go with a shovel and dig up 20 holes in a field, well, those 20 holes are just about as random as any other 20 holes. So you can say the sample is reasonably random. Or you can utterly disagree and say, nope, that the random selection has been violated, or the SRS is not given, or something like that. If you find that you're in the midst of a violation of assumption, or you think you are, go ahead and say so, but keep going. We can list all that as a limitation at the end. All right, the next one, this is a state university. I went to a state university. They're huge. So with a sample size of 200 for first-year students, I have a feeling that there's way more than 2,000 first-year students. So I think it's safe to say the population of all first-year college students at this university is at least 10 times the sample size. All right, see that word times, T-I-M-E-S? Don't put an X there, right? Don't do it, because that's not formal writing. Don't do that. Okay, the third thing we're going to check is normality. And we have to check that n times p hat is greater than or equal to 10, n times 1 minus p hat is greater than or equal to 10. Show those products. So 200 times 0.66, that's 132, check. 200 times 0.34 is 68, that's bigger than 10 too. So both exceed 10, so normality of the sampling distribution is approximated. Okay? Now, in the quiz, every other person who took it started talking about, oh, sample size is bigger than 30, it's normal. No, all right? Okay, that's your central limit theorem. That does not apply to proportions. It applies to means, not to proportions, all right? The n times p hat and the n times 1 minus p hat being bigger or equal to 10 is what gives you your, that verifies your normality. So no central limit theorem until we go to the next chapter. Got it? All right, so pause this if you need to copy this stuff down. All right, the next section is to show your calculations. First thing you might want to do is, and this is what AP really wants you to do, is name what you're doing. These will be results for a 1 proportion Z interval. Okay? And I also wrote this up here, right here. I guess I can't really point it out too much. Here, I'll circle it. That is just the bare bones of what we're doing. You don't have to write that down. This is just for notes. So we're going to build a confidence interval. We'll start out with our sample estimate, p hat, remember 0.66, plus or minus. All right, the Z star is how many standard deviations. In this problem, we're using the empirical rule, so Z star will be 2. For other confidence levels like 90 or 98 or 99, we're going to have to look up what the Z star value is, okay? But for now, we can just use 2. And then it's p hat times 1 minus p hat over n and take the square root. So here is your sample estimate, 0.66, and your standard error of p hat, square root of 0.66 times 0.304 over 200. That equals 0.033496. I like a little accuracy, so I went to a lot of decimal places. All right, here's how you build it. You name your interval with a capital C and a subscript 9.5. So that 9.5 could be a little smaller, but that's what it is. Equals your sample estimate, 0.66, plus or minus 2 for your 95%. Standard errors, 0.033496. And then if you do the math, you get your final answer, 0.593007 up to 0.726993. That's it. That's your confidence interval. Okay? So we're 95% confident that whatever the true proportion is in this school for kids that believe about that, financial well-being as being important falls in that interval. We're 95% confident, all right? This is just one interval out of a whole lot of intervals that we could have generated. Hopefully this is one of the 95% of them that's good, but it might not be. It could be one of the 5%. Well, that's the way life goes. So finish writing that. All right, so the next thing, and this is definitely a requirement, all of this is a requirement, we need to interpret our results with a formal statement, and this is the script. Ready? Go. We are 95% confident that the true proportion of first-year college students at this university who identify being well off as an important goal falls in the interval, and I shortened the numbers a little bit, from 0.5930 to 0.7270. Okay, I think the 4 places is pretty good. So take a moment and copy that down. All right, now I did include this. Remember I said up here that you might not be able to verify your assumptions? You can list them, but you may not be meeting one or more. Okay, if you feel that you have a violation and you've written that's violated, then here is where you put down your limitations, right? And you word it like this: possible violation of the whatever assumption, one of the three, or more than one of the three, may cause this result to be invalid. Don't write this if your assumptions are fine. Haven't you written enough, right? Don't please me by just throwing that in there. You know, say possible violations of assumptions may cause this result to be invalid. Why would you put that there if your assumptions are fine? So don't. So that's what the parentheses are, just to show that it's optional. All right, so what does 95% confidence mean? All right, now they aren't asking you this in terms of the problem we just answered. It's already answered. All those 4 steps is a complete answer, okay? This is just, you know, making sure you can inform somebody who's interested, maybe me, that you can tell me what 95% confidence means, right? It is not saying that you have a 95% probability that this captures the true p-value, because it either did or it didn't. That's 100% or 0%. There is no 95% about it, right? Because that implies that one moment it's good and another moment it's not, and that can't be. So, refer to the process. So this result is based on a method or a process that successfully estimates the true population proportion in 95% of all samples of this size. There it is. That's what it means. There are other ways to say it, but that's a pretty good way. So we're down to one more question, and this is just a separate question referring all the way back up here to that national survey and the 73% response that people are they're being very well off financially is an important personal goal. Well, here's what they're doing, and this is, I think, is really in many ways the most fascinating question of all of them. All right, look at your interval, basically 0.59 to 0.7269, right? Did you manage to capture 0.73, right? Well, you fell a little short. The high end is below that value. So the low end is clearly below it too. And the question is what we got up here good evidence that the proportion of all first-year students at this, university, kind of a smaller scope study, is that evidence that the students at this university who think being well off is important differs from the national value of 0.73? Well, this is like an inference question. And if 0.73 falls in here, then yeah, they're pretty much the same, from the university to those folks in the national survey. But since you missed capturing 0.73, this is good evidence that the proportion of all first-year students at this university who think being well off differs from the national value. And don't just leave it there. You have to say why, and it's because our confidence interval did not include that value, or 0.73. Isn't that amazing? That's just what I think is really special about what we're looking at now, because we can use a confidence interval to make judgments like this. Now, we didn't prove anything, but we have evidence. Remember court evidence? So, anyway, what I'm going to do now is you can pause and finish copying all this stuff, and I'm going to set up for a little demonstration to close this out. So I am going to go and pause this. So stand by. All right, hi guys, I am back, and this is actually a demonstration about means, but let's go ahead and just use it for just a generic confidence interval. The little box here is going to be where I can input things to change up the parameters and of the demo. And what you're going to see over here is a solid blue line going vertically right down the middle of this gray rectangle, and that'll represent our target parameter. And what's going to happen here, I'm going to change this to 30. We don't have to, but I'm going to test and produce 100 confidence intervals. And I'm going to start at 95%. And what I'm going to see here is around 5 of the 100 will fail to intersect with that parameter, the parameter line. And the other ones will. The ones that don't will be red, and the ones that do will be kind of gray. So let me hit test. All right, there's 100 and only 1 missed. Let's keep going. All right, 1, 2, 3, 4, 5. That's more like you'd expect. Now it will be variable because I can only do them 100 at a time. If I could do all of them at once, we could see that exactly 5% will not cross this blue line and turn out red, whereas the other gray ones are the good ones. Here's another one, that's 3. Here's another one, that's 4. Here's another one, 1, 2, 3, 4, 5, 6, 7. Okay, 3, that's 4 actually. You get the idea. Ooh, this is a lot. Okay, now I'm going to change things up a little bit. I'm going to drop this. We aren't ready to do this yet, but we will be able to after tomorrow. I'm going to drop the confidence level to 90%. And what will happen is if I'm lowering this to 90%, then I'm accepting less margin of error. All right, I'm going to lose some confidence here because I'm just going to shrink the interval, so more of them are going to miss. All right, so you'd expect 10 out of 100, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13. All right, that's probably more than 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. In the long run, we would probably average about 10 of these. Right? The width of these is smaller, and so we have less confidence. Right? Now I'm going to move this up to 99% confident. So we should expect just one red line, maybe 2 or 3, or maybe even none. So there's 1, there's 1, there's 4. There's none, there's none, there's 1. Okay, so what we've done here is we've taken the 90% or even the 95% and we've stretched them out so that it's a wider interval. So we're more likely to run into this blue line more often, okay? Which begs the question, what would it look like if we had 100% confidence? Because wouldn't it be nice to estimate things with 100% confidence? Well, here's what will happen. Since 99 is our widest confidence interval so far, in order to take that to 100% confidence, shouldn't the width of this line be infinite? Right? Because if it goes on forever from negative to positive infinity, we will definitely capture this blue line all the time. Right? Well, the downside is if you always capture the unknown parameter and you do it every single time and you know that this width of this interval is infinite, well, what exactly are you estimating? Because that value could be anywhere from negative to positive infinity, so you have no precision, right? So there's a payoff here. As you go down, like to say 90, you're going to miss out and have more failures, but the ones that hit will be more accurate, they'll be more precise. And what it amounts to here is if you just settle in at 95, that is kind of a nice sweet spot. You get a lot of precision and you get good estimations because you don't get results that miss estimating the true parameter like these 3 red ones do. So interesting. I hope that this has been somewhat enlightening, that this has given you a good start in this process. It can be a little bit hard. This is abstract stuff. The nuance is pretty intense. So if you have trouble with it, you're not understanding, see me. You can watch other YouTube videos. I'm sure there's some good ones. You can get a study buddy. We will help you through this. All right? So that was our lesson. Hopefully for you guys that weren't there, it was helpful. And for the rest of you, if you're seeing it again, great. So I will see you tomorrow, where we'll find out how to do these intervals with any confidence level. So good night. See you later.